All right, so this is a mini lecture by Jared Nimi on simple random sampling. Okay, all right, so I pulled a data set to work with here. I am not used to surveys whatsoever, and so this data set that I pulled was from an analysis that was done on this. This is actually done for showing you how to use Stata to do survey work. And this data set happens to be for all California public schools that have more than 100 students. And so it turns out that there are 6,194 of them, and there's 757 school districts. And the variable that we're going to be interested in for the purpose of this lecture is the academic performance index. All right. What's that? This data was just on the site. Yep. Okay, so right. So we're interested in particular, we're going to be interested in estimating the mean academic performance index across the entire population, that is, this entire 6,194 schools. Right? And so what we're going to do is we're going to take samples from it and then see how we use that sample to estimate that mean. Right? Since we only have 6,194 and since we actually had all the data, right, we would just calculate the mean, which is the first thing we're going to do so we can check our answers. Right? But the idea here was, what if it was expensive to go and calculate this academic performance index for all schools, and instead of doing all schools, you just wanted to do some subset? And what could you say about the overall academic performance index given only a subset? And I mentioned, in particular, what you might want to know is whether a particular school is over or underperforming that index. Okay. All right, so this is just a quick summary of the data. There's a whole bunch more in this data, so it could be a very complicated data set to analyze. Initially, I was planning on doing stratified random sampling here as well, and I probably will put up a lecture on that afterwards, but I didn't get to it, and we probably won't have time anyway. So right now, all right, so I can provide this data set on the website, so you don't have to find where to actually download it from. And it happens to be a Stata data set, which turns out you can read in using this foreign library. I just pulled off 3 columns here. The first one is just the academic performance index, I assume in the year 2000, thus the 00. We have the district number. Right? There were, 757 districts, I think it said. And then this is the type of school, so whether it's an elementary, high school, or middle school. So that was what I was going to use later to do some stratified and cluster sampling, but I didn't get to it yet. All right, so again, the idea here is that what we're really interested in is estimating this from a sample of schools. So our objective here is just to get the number 664.7, right? Some uncertainty around it. All right, so I recalculated it there because I forgot that it was in the summary table. And then I just decided to plot, just to see what it looked like, all of the APIs for all the schools. And on top of that, I plotted the best fitting normal curve. That is, I found the mean and the standard deviation of that data set and plugged it into the dnorm function at R just to get the best fitting normal curve. So what do you guys think about how well that data fits a normal curve? What's that? Not good. Why not good? So what's that telling you? Yeah, so I agree. Right? This is low here relative to what you'd expect to see. You could test that by doing random simulations of 6,194 data set from a normal distribution and compare it to the actual curve. And you'll see with 6,000 data points, you get a really good approximation to a normal curve if the data are in fact normal. Okay, so what does that tell you, the fact that it's low here? We do not necessarily need to go Bayesian. Yeah. So the suggestion over here was use a T, and in fact the answer is the exact opposite. So with a T distribution, right, the key thing with the T distribution is you have heavier tails, right? And what you're going to see with heavier tails is, in fact, a peak right here. Right? You're going to go over the normal curve. So test that out by simulating from t-distributions and overlaying the best fitting normal curve. Right? You see a peak here, and then you see more weight down here. So what we actually have is the opposite. We have, it's less here, right? And it's less here. So in fact, we have light tails, not heavy tails. Why might we have light tails? Yeah, I think that's the most likely explanation for why, why there is likely lightened tails is that this scale maybe for the API is only, say, 300 to 1,000. So you can't possibly get observations that are bigger or higher than that. That's certainly one way you can get light tails. Yes?
Yeah. Well, originally off of this point, what about a beta distribution, a scale beta?
Oh, so yes. Well, and this is the other. We don't have to go Bayesian, right? But if we really wanted to model this data, we might want to choose a distribution that has properties that look like this. So certainly, yes, you could do a scaled beta. You know, you could do a truncated normal, right? You could do other things, but anyway. So the point here is just we're going to use the normal distribution later, and I just wanted to point out the data clearly aren't normal, and yet when we use the normal distribution, it's going to be totally fine. Okay. All right. So this is the data we're trying to. In particular, we're trying to estimate this overall mean, 664.7. All right. So let's let yi represent the API index for school I, and we have capital N of those. That's 6,194 in this data set. And if we don't have any other information about the schools, right? I already did show you some other information. We know school district. We know the type of school, elementary, middle, or high school. But if we assume we didn't have that information, then it would make sense to model the schools exchangeably. Right? And if we think that the schools are exchangeable, then we can sort of use Di-Finetti's theorem to say, well, there might be, we can take the marginal distribution for the data. Right? This is the joint distribution for all the data. And assume that there's some prior, right? Di-Finetti's theorem says, at least as n goes to infinity, there's some parameter theta and some prior over that parameter such that the data become independent, conditional on that parameter. Right? So we haven't now specified the distributions for y given theta or the prior for theta. But we can use this idea in a second. And the other thing that we're going to use is to have an indicator of whether the school is in the sample or not. Right? So here I is a vector of the same length as y, and it's just 1 if it's in our sample and 0 if it's not. Okay. All right, so now we have to decide how we're going to sample. I said the first thing we're going to do is just pretend we have a simple random sample from the whole population of schools, and we're going to take small n of those schools. Okay. So it turns out we can write this down, this probability of inclusion in this notation. But the key thing is that this probability of inclusion doesn't depend on any covariates or the observed data. Right. And so this sampling design is ignorable. Right? And the key thing here is that, well, a key terminology in the survey literature is called the propensity score. And this is just the probability of that sample being included. In this case, it's just small n, the number of schools we're sampling, over the total number of schools that we have. Okay. All right, so the quantity that we're interested in is we have taken a sample. Let's assume we've taken a sample now. And so we have a mean over those schools that we actually have in our sample. That's y bar obs. Right? So this is the 20. I haven't said yet, but we're going to take a sample of 200. So this is take the 200 schools, calculate their average. That's y obs bar. And then we have the average of all the data that we didn't include in our data set. That's going to be y bar miss. And now we just have to, in order to calculate the quantity that we're interested in, we have to take the weighted average of our observed and our unobserved, which of course we don't know, where the weights are just the proportion of schools that we took and the proportion of schools that we didn't take. Okay, so we're going to use this later. I think it's so far away over there. This is going to be important to remember or to, yeah, maybe I should just write it down. All right, so we have y bar is equal to little n over capital N, y bar obs, plus capital N minus n over capital N, y bar miss. Okay, so we're going to come back to this. Okay. So, but that's the quantity we're interested in, is y bar, right? That's the average over the whole data set. Is that clear why that's the average over the whole data set? Weighted averages are key. Okay. Oh, there's what I just said. Y bar miss, the average of the school is not in the sample. So I'm not going to talk now about two different ways of estimating that quantity. I'm going to talk about a simulation approach and then an approach based on large sample theory. Okay. The simulation approach is sort of going to be more general, and it shows sort of a computational approach to the problem. And the large sample theory is going to work when big N and little n are both getting large. Okay. All right, so for do this particular simulation approach, you actually need to specify a distribution for your data conditional on some parameter, and then you have to specify a prior for that parameter. Right? So if you do that, then you can write down, because the design is ignorable, do I say that some? Because the design is ignorable, we can actually estimate the posterior distribution of that parameter only using the data that we actually observed. And that's, again, because the design is ignorable. If it was not ignorable, then we could not do that. All right? So then, as long as we've chosen a distribution here that we can actually sample from, right? So this is the distribution for how the data arose, which I'm going to use in this example as being a normal distribution, even though we've already talked about limitations of the normal distribution in terms of how to model, in terms of using a normal distribution to model this data. All right, so the idea here is to do this, right? This we have, that's known. This we don't have, but what we're going to do is we're going to simulate it, right? And what we're going to do to simulate it is a very brute force approach, just to simulate all the missing data, right? So here's the idea. We're going to simulate the missing data. I should say here, yeah, I should make it clear that this is I. Okay, so I make it clear here. So the observed data go from 1 up to n, and then the unobserved data, or the missing data, go from n plus 1 up to capital N. All right, so all the yi's, n plus 1 up to capital N, are unobserved, and so we're going to sample them. And what we're going to do is, for each sample in our posterior distribution for theta, right, so we're going to sample from the posterior, possibly using an MCMC, sample theta, plug theta in here, and now sample a whole set of missing data. So in this case, 6,194 minus 200. Right, sample all the missing data, and then calculate the average of those missing data. Is it clear why it's a very brute force approach? Because we're simulating for every data. I heard somebody say during the team rat that why don't we just treat the missing data as parameters, and that's exactly what we're doing here. Right? All the missing data are treated exactly the same way as any other parameter, for example, theta. And the prior on the missing data is just our model. Right? Okay, so we go ahead and sample missing data, calculate the average, and we do that over a whole bunch of draws from our posterior for theta. And again, this could be independent Monte Carlo draws, or they could be MCMC draws, and it doesn't matter. Either one would work. Okay. Once we have those draws, we just plug y miss from those draws into the formula, and now we have a whole distribution for y bar. Right? One for every iteration in our MCMC, or one for every draw of theta, however we got it. That makes sense? I see quizzical looks, so I think that we should make sure that this makes sense. All right, so just to repeat. Let's say we're doing an MCMC, right? In each iteration of the MCMC, we have a draw for theta, right? So this is for iteration j. So we have a draw for theta. For every draw for theta, we're going to draw a whole set of missing values, right? We're going to impute, if you will, all the missing data. So we're going to sample, again, 6,194 minus 200 of these values at every iteration in our MCMC. Given those draws, we're going to calculate their average. Right? So now for every iteration in the MCMC, we have a draw from y bar miss. Yep?
What is that y, I in there?
This is just whatever distribution you assumed for the data. Right? It's the same distribution you assumed for y obs as for y miss. So for instance, in what I'm going to show you, it's going to be a normal distribution.
So do we simulate a value from that and then do it for each value of the yi? Do we simulate from yi's from I guess.
Right, so for instance, let's assume that theta here is a mean and a variance for a normal distribution. And so we assume that our data conditional on the mean and variance are independent. Right, now we're going to sample all of the missing data from a normal distribution with mean whatever we had in that iteration in the MCMC.
So then each y sub I is 6,000 minus 200.
No, so the I here is indexing school. Right, so this is for school I for iteration j. And I then runs from n plus 1 up to n, which is all the different missing data. So yeah, so this is going to be, this is a scalar, but you have a whole collection of them. Right? You have about 6,000 of them. And with those 6,000, approximately 6,000, you're going to calculate their average. Right? That's for each iteration of the MCMC. With that value, you're going to plug it into this equation, and now you have a sample from the posterior for y bar. And with that whole collection over all the iterations, you have now a distribution for y bar. Okay, so imagine what happens as n goes to infinity, capital N goes to infinity, right? It's going to become computationally intractable because right here you're sampling from n plus 1 up to capital N, and if n is, a billion or 350 million or something like that, this isn't going to be so feasible. But nonetheless, it defines a very generic approach to performing data analysis with missing data. Right? The idea is just impute the missing data. And then typically, calculating quantities based on the complete data is easy. Right? So this doesn't have to be the mean. This could be any quantity you want. It could be the median. So you simulate the missing data, and you use the observed data, and you calculate the median. Right? It could be a quantile. It could be whatever you want it to be. Okay? So it's very generic, but as I mentioned, can be computationally expensive if capital N is large. Okay. All right, so that's fine. We could use a simulation-based approach. In this example, we could use large sample theory. So we need to recall our central limit theorem that says that, okay, so this is now conditional on theta. So if you knew the parameters of the distribution, well, yeah, in this case, it's not going to matter. All you're going to need to know, this is the key. You need to know the expectation of your data, and you need to know the variance. And of course, the variance has to be finite. And if you have that, then the central limit theorem kicks in as long as the number of missing data is large. Right? If you have a large amount of missing data, then the average of their values is just this formula by the central limit theorem. Or it's approximately. Right? It converges as n minus n goes to infinity. So this is just an application of the central limit theorem to your missing data. Okay. So now essentially what we're going to do is we're going to integrate out theta. All right, and we're going to do this now as little n goes to infinity. Right, this is as the amount of missing data goes to infinity, and this is as your sample gets larger. Right? So as your sample gets larger, then we have this. Right? So notice that this conditional distribution depended on these population parameters, mu and sigma squared. This distribution here is going to depend on, it should really say on y obs. The bar shouldn't be here, because s obs depends on actually y obs. Right? So this is going to depend now on the data you actually observed. Right? So the missing data, given the data you've observed, has a normal distribution centered at the observed data mean. And with variance, that is this function where s obs here is the sample variance of the observed data. And basically the idea here is as your sample gets large, you just plug in your estimators from mu and sigma squared. Right? That's the idea. Right? So your estimator for the population mean as your sample gets large is just y obs. Your estimator for sigma squared, yeah, so what's, oh, right. This is where we needed this. Right? No, we're still at y miss. Okay. As n goes to infinity. All right, well, anyway, we're running out of time. So verify that this makes sense to you. The next part is what I was going to show is down here. All right, so now the idea is that you have, if you remember this formula, you have y miss as being a normal distribution, right, according to that central limit theorem. And you're trying to find the distribution for y bar. Well, this right here is just a constant, right? And this right here is a normal distribution. And so a constant plus a normal is just going to be another normal. Right? Its mean is going to be this weighted average of the mean of this and the mean of that. Well, the mean of this is just itself. The mean of that is y bar obs. Right? So y bar obs is just y bar obs. The variance, right? This is a constant, so it has no variance. You have the variance of this times this quantity squared. Right? And that gives you that equation right there. Okay, so let's see, no. So that's the large sample theory. So the point here is that if n minus n is large, right, we're pretty large there, we're about 6,000. If the number of samples you have, n, is large, right, we have 200. What do we normally tell intro undergrad students for how big is big enough for the central limit theorem to apply? 30, right? Okay, so we seem to be okay there. All right, so then we can use this formula. And now we have an approximation to the actual posterior for y bar, given by this normal right here. Okay. All right, so this is the R code. I'm just going to point out here's the statistics you need to do the large sample theory. This is where I've assumed that the observed data and the missing data are both normal with the same mean and variance. I simulate, right, what this is going to do right here is to actually simulate the missing data. And then given that missing data, I'm going to calculate its mean and plug it into this formula so that y bar is going to be a draw from the posterior for y bar. Now this is actually a draw from the true posterior, but where we've assumed that it's normally distributed, and we've assumed that these priors, which are diffuse proper priors. Okay. All right, and then I run it. I pointed out here that I did actually check that it converged. It converges pretty quickly. And then I used the JAGS sample function. Oh, this shouldn't be here, because that's not going to work. That gives you the error. OK. So here's the differences. So right, our large sample theory says here's the normal distribution. That's the black line. Our simulations here are, this is the smooth version, a kernel density estimate of our histogram. But that's the posterior under this simulation-based approach. Is the blue line. And the red line is the truth. Okay. So in particular, the key thing is that, right, even though the large sample theory and the blue lines were based on different assumptions, right, the large sample theory says we have n minus n is large and n is large. It's large enough that the central limit theorem kicks in. The blue line says we don't need that assumption. But we did have to assume that the data are normally distributed and these priors that were diffuse, proper priors on the parameters. Right? And they basically give you the same answer. Right? This wiggliness is just Monte Carlo error. If you drew more samples in your MCMC, this blue line is going to get pretty much closer and closer to the black line. Okay. All right, so I think this just says exactly what I said. Right? If you have large N and large amount of missing data, then you can use the normal theory inference that we talked about, and no assumption is needed about the distribution of your data. But if you don't have that, then you can make an assumption, or you must, if you want to do this approach, make an assumption about your data and a prior for the parameters in that model. But then you can always use a simulation-based approach where you impute the missing data at every iteration.